Today we're going to talk about section 1.6, absolute value equations and inequalities. First, a definition of absolute value. Some of you may have heard this from previous years in math, but absolute value is the distance a number is away from zero. A distance from zero, especially on a number line, obviously helpful. And we use these symbols right here. Absolute value of 4 is equal to 4, absolute value of negative 4 equals 4 because 4 is 4 units away from 0. Negative 4 is 4 units away from 0. And the symbols here, the absolute value of x equals x if x is greater than or equal to 0. X is equal to negative x if x is less than 0. These will come in handy later on. So let's take a look at our first example here. What is the solution for this absolute value of 2x minus 1 equaling 5? Remember, it's going to have two solutions because it's an absolute value problem. So what they've done is split it up into two problems. First one, they just dropped the absolute value symbols. The second one, they dropped the absolute value symbols and set it the negative 5 here. In other words, we're taking the opposite of what its solution is. Positive 5, negative 5. We always take the opposite of it. Since we have two equations, we're now going to go ahead and solve those. We solve for x minus 3 here and x minus 2. You might have noticed also that the word or came up here. Now this is similar to the or and statements, but just for our purposes right now, we know that we have two solutions. Either x will equal 3 or x will equal negative 2. Here's our next example. We'll do this one together. Squeeze up our little number line. So let's go ahead and solve this one. First, we know we have to split it up into two problems. So we're going to drop the absolute value. And then we're going to drop the absolute value again. And then set it equal to the opposite of whatever this is. Then solve. Subtract 2 from both sides. Then divide by 3. Subtract 2 from both sides. Remember, minus 2, negative 4 minus 2 is going to leave us with negative 6 divided by 3. So we can have this solution, 2/3, or negative 2. So I'm going to go to negative 2, make my dot, go down to 2/3, somewhere between 0 and 1, closer to 1, and there's our solution. Remember, these are just equations, so we're going to have just dots as our solution set. Let's take a look at multi-step absolute value equations. Now, if you notice, this one here has something hanging on the back here and out in front, and it's a little bit different than what we had here. This absolute value is all by itself. So our goal for the next one is to get this absolute value all by itself. In other words, we're going to isolate the absolute value. First thing, we're going to work with PEMDAS in reverse. And that's going to be in reverse. Some people call that SADMEP. They're both funny words. So our first step is going to be addition, subtraction. So there's my subtraction. So I'm going to do the opposite, add 1 to both sides. Then I'm going to get the absolute value by itself by dividing both sides by 3. Just as before, since we have the absolute value by itself, we're going to split it up into two problems. Drop the absolute value. Drop the absolute value and set it equal to the opposite. Solve for x, subtract by 2. Solve for x, subtract by 2. And remember, again, this is an OR statement. So on the number line, we're going to go to 1, put our dot, and -5. Our next item is that we've got a definition here that we definitely would like to put into our Cornell notes, right here, is of an extraneous solution. It is a solution derived from an original equation that is not a solution of the original equation. That may sound funny, but here's another way of looking at it, is that we will go ahead and solve for x and use all the legal methods we have in mathematics, but one of the answers, or both of the answers, may not work for the original equation. Let's take a look at what an extraneous solution might look like. Again, we have our absolute value isolated. That's good. We've got a couple extra things here. We'll get to that in a second. Let's go ahead and split that into two equations. We're going to have 3x plus 2 equals 4x plus 5. Second one here, again, drop the absolute value. And you might be guessing or thinking, what am I going to put here? Well, as before, we said we're going to take the opposite of whatever this is, and that's exactly what we're going to do. Take the opposite of 4x and take the opposite of positive 5. Isolate your x. In other words, we're going to move all the variables to one side. Subtract 3x. Get the x by itself. Subtract 5 from both sides. Here, we're going to work with the lowest term for our x variable. -4 is our actual lowest term. So we're going to go ahead and add 4x to both sides. And we're going to have 7x plus 2 equals -5, and solve as we normally would for x. Now the way to check for an extraneous solution is to plug these back in and see if they work. We're going to plug in -3 and see if it is a true statement. We're going to plug in -1 to see if we get a true statement. And again, we're going to plug it back into the original absolute value. So let's try the first one here. This will be -9 plus 2, which is going to be -7. And then we're going to have -12 here plus 5, which is -7. Now the question is, what's the absolute value of -7? Well, -7 is 7 spaces away from 0. It does not equal -7. So here, since this is not true, this is an extraneous solution. Whoops. Let's check the next one. Absolute value of 3. This is going to become -3 plus 2. That's going to be -1. And we're going to have -4 plus 5. and that's going to equal 1. And sure enough, the absolute value of negative 1 does equal 1, and that is one of our actual true solutions. Now you get the joyous task of trying this one here on your own in your Cornell notes. Our next stop with absolute value equations and inequalities is actually talking about the inequalities. As you can see, the only difference between the previous absolute value equations and this is the inequality sign. Same rules apply, but again, anytime you have a inequality, you've got to take care of that. If you have any negatives on both sides, you need to multiply or divide. Let's take a look at our first one. Is our absolute value isolated? The answer is yes, so let's split it up into two problems. Some technical difficulties again. I think the technical difficulties is in my brain. If you guys are listening to this, hopefully you guys get some sleep tonight. Very helpful. We're going to have another inequality over here, and that's going to be negative 5. Now, if you think about it, since we've changed the sign of this 5 to negative 5, we probably have to change the inequality sign. And that's exactly what we have to do. This was less than, and we're going to have to switch this to greater than on this side. Now, let's determine if this is an and or an or statement. Since this is a less than, it sometimes sounds like less than to some people. And that might be a good little silly reminder that this is an and statement. If this was a greater than symbol, sometimes people are reminded by this. Instead of greater than, it's greater than. Again, silly, but effective. So since we started off with a less than statement, that means it's going to be an and solve as usual. And then we get to graph these. Go to 3, and that's going to be open. Go to negative 2, and that's going to be open. Shade to the right for, to the left for negative 3 Shade to the left for 3. And shade to the right for negative 2. And if you recall, when it's an and statement, we are looking for the overlap. And sure enough, here is our real solution right here. All the numbers non-inclusive between negative 2 and 3. Our last example here is an or statement, as we said. And the reason I know it's an or statement is because of the greater sign, greater than or equal to. And here are the solutions to these. X is going to equal, greater than or equal to 1, and x is going to be less than or equal to negative 5. And as we said, typically or statements do go in the opposite directions of each other. So the solution here would be any number greater than or equal to 1 and less than or equal to negative 5.